1956. Longview, Texas. The engineering calculations spread across R.G. LeTourneau's drafting table would have horrified efficiency experts from across the Atlantic. 1-inch thick steel plate where European designs called for 3/4 inch. 13-foot tall tires housing 90 horsepower electric motors. Planetary drives built for 12 miles per hour maximum speed when competitors pushed 25. Through the Texas heat and factory noise, welders reinforced every frame joint with half-inch gussets that European consultants dismissed as wasteful American excess. Dr. Heinrich Müller from Krupp had already declared the approach engineering ignorance. Too much steel, too much weight, too much everything. In European factories, precision optimization ruled. Every pound of material served a calculated purpose. Machines built to exact specifications delivered promised performance on controlled test tracks, maximum efficiency through minimum waste. The Americans were building earth-moving scrapers using philosophy the Europeans considered primitive and financially reckless. Oversized everything, over-engineered frames, overpowered drives that forgave operator mistakes rather than punishing them. Across an ocean from European precision, the most enduring construction revolution in American history was taking shape, not through efficiency calculations, not through material optimization, but through the stubborn conviction that some machines should be built larger than the problem they're meant to solve. The morning of June 29, 1956, President Dwight Eisenhower lifted his pen from the Federal Aid Highway Act, authorizing what would become the largest earth-moving project in human history. 42 billion cubic yards of earth would need moving to carve 41,000 miles of interstate highways across the American continent. The numbers staggered even seasoned construction executives who had built airfields across the Pacific during World War II. To put the scale in perspective, the entire Panama Canal had required moving only 240 million cubic yards of earth over 8 years. The interstate system would demand 175 times that volume in half the time. Within weeks of the signing, construction companies across America confronted a brutal reality. Their existing earth-moving equipment simply could not handle the volume. Farm tractors pulling scrapers crawled at 8 miles per hour, requiring 16 hours to complete what the project timeline allocated for 10. Bulldozers designed for clearing farmland broke down under the punishment of moving frozen clay in Minnesota winters and baked hardpan in Arizona summers. The mathematics were unforgiving. At current equipment capacity, the interstate system would require 30 years to complete instead of the mandated 15. European engineering consultants arrived in New York and Chicago, harboring typical post-war confidence in their technical superiority. They carried leather portfolios filled with stress analysis charts, efficiency calculations, and photographs of sleek earth-moving machines operating on German construction sites. Dr. Heinrich Müller, representing Krupp's construction equipment division, addressed a packed auditorium at the Conrad Hilton Hotel in Chicago. His message was direct and condescending. American earth-moving equipment represented primitive over-engineering, he declared, wasteful excess that ignored modern scientific optimization. European machines achieved 15% better fuel economy, 20% faster cycle times, and 30% lower material costs per cubic yard moved. The German presentations impressed corporate executives eager to modernize their operations. Detailed charts showed how European scrapers used precisely calculated steel thicknesses, optimized gear ratios, and advanced hydraulic systems that eliminated the massive mechanical components favored by American manufacturers. Where American scrapers weighed 34,000 pounds empty, equivalent European models achieved identical earth-moving capacity at 26,000 pounds. The mathematics seemed irrefutable. Less steel meant lower costs. Lower weight meant better fuel economy. Scientific optimization meant superior performance. Construction companies began placing orders for European-designed equipment, often manufactured under license by American factories, but built to European specifications. The first machines rolled off assembly lines in Detroit and Milwaukee, looking remarkably different from their American predecessors. Sleek profiles replaced boxy frames. Thin-walled steel tubing substituted for solid plate construction. High-speed transmissions capable of 25 miles per hour maximum speed replaced the sluggish 12 mile per hour American standard. Engineers at Caterpillar and other American manufacturers watched nervously as their traditional designs suddenly appeared antiquated. The early field tests seemed to validate European confidence. On controlled demonstration sites outside Chicago and Los Angeles, the imported designs performed flawlessly. They moved Earth faster than American equivalents while consuming less fuel. Trade magazines published glowing reports about the scientific approach to Earth-moving equipment design. Industry experts proclaimed the end of American over-engineering and the dawn of precision-optimized construction machinery. Then winter arrived. The first catastrophic failures occurred on Interstate 80 construction through Nebraska, where temperatures dropped to 20 below zero and stayed there for 6 weeks. European-optimized scrapers that had performed brilliantly during autumn testing began experiencing frame cracks after only 800 hours of operation. Thin-walled components designed for German climate conditions buckled under American temperature extremes. Hydraulic systems optimized for efficient operation failed completely when exposed to the relentless pace demanded by American contractors working 16-hour days, 7 days a week. Contractor Jake Morrison, building a 12-mile section east of Lincoln, Nebraska, found himself operating an inadvertent laboratory. Half his fleet consisted of European-designed machines, the other half traditional American over-engineered equipment. His maintenance records told a devastating story. The efficient European models required major repairs every 800 to 1,000 hours. Hydraulic pump failures, transmission breakdowns, and frame fatigue cracks plagued the supposedly superior designs. Meanwhile, his American-built scrapers, dismissed as wasteful dinosaurs, continued operating past 3,000 hours with nothing more than routine maintenance. Morrison's testimony at industry meetings became legendary among contractors. The German machines were engineering marvels when they worked, he would say, but they worked only under ideal conditions that rarely existed on American job sites. American machines were engineering hammers that always worked, regardless of weather, operator skill, or maintenance schedules. His cost per cubic yard calculations showed that despite higher initial purchase prices, the over-engineered American machines delivered 40% lower operating costs over their service lives. Dr. Muller, facing mounting evidence of his optimization theories failing under American conditions, doubled down on his criticism of American engineering philosophy. At a heated industry conference in Detroit, he dismissed field failures as operator error and maintenance neglect. Americans, he argued, simply did not understand proper equipment operation. European machines required skilled operators and scientific maintenance schedules. American over-engineering merely compensated for operational incompetence. The accusation infuriated American engineers and contractors who understood their equipment faced conditions European designers had never imagined. Frozen ground that shattered optimized components. Operators working exhausted 16-hour shifts who made mistakes that machines needed to forgive. Construction schedules that allowed no time for the careful maintenance European equipment demanded. The fundamental philosophical divide became clear. Europeans built machines to work perfectly under ideal conditions. Americans built machines to work adequately under terrible conditions. By winter's end, the full scope of the challenge crystallized. America needed earth-moving equipment that could survive American conditions, operated by American workers, under American construction schedules. The question remained whether American manufacturers would abandon their traditional over-engineering philosophy in favor of European optimization or trust their instincts about building machines tough enough to complete the most ambitious infrastructure project in human history. R.G. LeTourneau arrived at his Longview, Texas manufacturing facility each morning at 5:30, carrying a thermos of black coffee and a rolled set of blueprints that would horrify efficiency consultants. Despite selling his earth-moving empire for $31 million 3 years earlier, he remained obsessively hands-on, appearing daily at his drafting table to sketch solutions that defied conventional engineering wisdom. His 5-year non-compete clause with Caterpillar would expire in 1958, but LeTourneau could not resist developing concepts that challenged everything European consultants proclaimed about scientific optimization. The electric wheel concept emerged from LeTourneau's fundamental disagreement with speed-obsessed European designs, where competitors built scrapers capable of 25 miles per hour maximum speed. LeTourneau envisioned machines that moved at farm tractor pace but delivered unstoppable torque. His revolutionary design placed 90 horsepower electric motors directly inside 13-foot-tall tires, eliminating the complex mechanical drivetrains that European engineers considered essential. The concept seemed backwards to industry experts accustomed to high-speed efficiency, but LeTourneau understood something his critics missed. Construction sites punished equipment through constant acceleration, deceleration, and directional changes, not sustained high-speed operation. LeTourneau's frames used 1-inch thick steel plate where European specifications called for 3/4 inch. His planetary final drives were sized for 12 miles per hour maximum speed, creating massive gear reductions that multiplied torque beyond anything competitors offered. When critics questioned the excessive weight and material costs, LeTourneau's response became his engineering philosophy. He would rather build one machine that lasted 20 years than 5 machines that lasted 4 years each. The mathematics of durability, he argued, trumped the mathematics of initial efficiency. 300 miles northeast in Peoria, Illinois, Caterpillar chief engineer William Noss faced intense pressure from efficiency consultants who had gained influence with corporate executives following the European equipment demonstrations. Detailed cost analyses showed American over-engineering wasted 40% more steel per cubic yard moved compared to optimized designs. Board members questioned whether Caterpillar's traditional approach remained competitive against sleek European models that promised lower operating costs and higher productivity. Noss had risen through Caterpillar's ranks during World War II, when American manufacturing priorities focused on building equipment that worked under impossible conditions rather than achieving theoretical efficiency. His engineering degree from Purdue provided formal training, but his real education came from visiting job sites where Caterpillar machines operated in Montana blizzards, Arizona desert heat, and Pacific Island coral that destroyed cutting edges in hours rather than weeks. European consultants showed impressive calculations based on German test track performance, but Noss knew American construction demanded machines that survived conditions no test track could replicate. The engineering battle intensified during design meetings for Caterpillar's next-generation scraper line. Efficiency consultants presented compelling arguments for adopting European optimization principles. Thinner steel sections would reduce weight and improve fuel economy. Higher speed transmissions would increase cycle times and productivity. Advanced hydraulic systems would eliminate the massive mechanical components that characterized American over-engineering. The proposed changes would position Caterpillar as a modern, scientifically advanced manufacturer, rather than a builder of antiquated heavy machinery. Noss countered with field reports from contractors operating in conditions European designers never experienced. Frozen Minnesota clay that shattered, optimized components designed for moderate climates. Inexperienced operators hired during the construction labor shortage who made mistakes that required forgiving equipment design. Maintenance schedules compressed by relentless project deadlines that allowed no time for the careful attention European machines demanded. His argument was simple but profound. Caterpillar machines worked in Montana winters and Arizona summers, while European designs worked on German test tracks. The technical innovation that would define American earth-moving philosophy emerged from this philosophical divide. LeTourneau's electric wheel concept pioneered planetary final drives sized for farm tractor speeds rather than European high-speed designs. Critics mocked the slow American approach, but the massive gear reductions created torque multiplication that made machines virtually unstoppable under load. Where European scrapers stalled in tough digging conditions, American machines continued pulling regardless of ground hardness or operator skill level. LeTourneau's manufacturing specifications reflected his conviction that machines should be built larger than the problems they were meant to solve. His scrapers weighed 8,000 pounds more than European equivalents, but the extra weight came from structural reinforcement that prevented the frame fatigue plaguing optimized designs. Half-inch steel gussets appeared at every frame joint instead of the quarter-inch European standard. Hydraulic cylinders were sized to handle twice their rated loads, providing safety margins that eliminated the catastrophic failures occurring with precisely calculated components. At Caterpillar, NOS translated similar philosophy into manufacturing reality. The company's DW21 scraper specification called for 34,000 pounds empty weight compared to 26,000 pounds for European models. Factory workers welded half-inch gussets at frame joints, where competitors used quarter-inch reinforcement. Transmission cases were cast with walls twice the thickness European stress analysis indicated necessary. The additional material costs infuriated efficiency consultants, but Naus understood the true economics of earth-moving equipment. The American approach reflected fundamental differences in operating philosophy between European precision and American pragmatism. European engineers built machines to work perfectly under ideal conditions with skilled operators and scientific maintenance. American engineers built machines to work adequately under terrible conditions with exhausted operators and deferred maintenance. The distinction would prove decisive as interstate construction accelerated and contractors discovered which philosophy survived the punishment of America's most ambitious infrastructure project. By late 1957, both LeTourneau and Caterpillar had committed fully to their over-engineering philosophy despite mounting criticism from efficiency advocates. The true test would come when contractors compared long-term operating costs rather than initial purchase prices. But that vindication remained years away, as European consultants continued promoting optimization theories that looked impressive in boardroom presentations but had never survived a Minnesota winter. Production lines at Caterpillar's Peoria facility transformed throughout 1957 as William Naus implemented his over-engineering specifications despite mounting corporate pressure to adopt European efficiency standards. Factory workers received new welding instructions that seemed excessive to supervisors accustomed to optimized manufacturing processes. Every frame joint on the DW21 scraper required half-inch steel gussets instead of the quarter-inch reinforcement European design specified. Transmission housings were cast with double wall thickness compared to stress analysis calculations. Hydraulic cylinders were sized to handle twice their rated working loads, creating safety margins that efficiency consultants dismissed as wasteful redundancy. The manufacturing philosophy created immediate friction on the factory floor. Seasoned welders questioned orders to use twice as much steel as engineering calculations indicated necessary. Production supervisors worried about material costs that exceeded European competitors by 40%. Quality control inspectors measured frame components that weighed 8,000 pounds more than equivalent European models, wondering if American customers would pay premium prices for machines that appeared unnecessarily robust. The tension reflected deeper uncertainty about whether American over-engineering remained viable in an increasingly competitive marketplace. Meanwhile, in Longview, Texas, R.G. LeTourneau pushed his electric wheel concept toward production readiness despite skepticism from dealers who questioned demand for unconventional earth-moving equipment. His 13-foot-tall tires housing 90-horsepower electric motors defied industry conventions that favored mechanical drivetrains and high-speed operation. LeTourneau's planetary final drives were sized for 12 miles per hour maximum speed, creating massive torque multiplication that critics considered unnecessary for modern construction applications. The slow-speed philosophy contradicted European emphasis on cycle time optimization and productivity measurements that dominated trade publications. LeTourneau's frame specifications reflected his conviction that construction equipment should forgive operator mistakes rather than punish them. 1-inch thick steel plate formed the main structural members, where European designs used 3/4-inch thickness. Reinforcement ribs appeared every 18 inches along load-bearing sections instead of the 30-inch spacing European stress analysis recommended. The additional steel added 12,000 pounds to empty weight and increased manufacturing costs by 35%. But LeTourneau remained convinced that durability economics would ultimately vindicate his approach. The first validation came from an unexpected source. Jake Morrison, building 12 miles of Interstate 80 through Nebraska's Platte River Valley, found himself operating the construction industry's most comprehensive equipment comparison study. His fleet included 6 European-designed scrapers manufactured under license by American companies and 6 traditional American over-engineered machines built to pre-war specifications. Morrison meticulously tracked maintenance costs, downtime hours, and productivity measurements for each machine, creating detailed records that would influence equipment purchasing decisions across the industry. Morrison's initial results seemed to support European efficiency claims. The optimized scrapers achieved 15% better fuel economy during their first 500 operating hours. Cycle times averaged 12% faster due to higher maximum speeds and more responsive hydraulic systems. Material costs per cubic yard favored European designs by 18% when calculated over the first 1,000 hours of operation. Trade magazines published Morrison's early findings as validation of scientific optimization principles over American over-engineering traditions. The turning point occurred during Nebraska's brutal winter of 1957 to 58, when temperatures remained below zero for 6 consecutive weeks and frozen ground tested equipment beyond any European design parameters. Morrison's European optimized scrapers began experiencing catastrophic failures at 800 hours of operation. Frame cracks appeared along stress concentration points that German engineers had calculated as adequate for normal loading conditions. Hydraulic pumps designed for temperate climates failed repeatedly when exposed to extreme temperature variations. Transmission components optimized for efficiency could not handle the shock loading that occurred when scrapers bit into frozen clay. Morrison's American over-engineered machines continued operating through conditions that disabled their European counterparts. The massive frame showed no signs of fatigue cracking, despite punishment that exceeded any manufacturer's design specifications. Simple cable-operated controls functioned reliably, while sophisticated hydraulic systems on European machines required constant repair. Planetary drives sized for farm tractor speeds delivered unstoppable torque that pulled loads European machines could not handle. Morrison's detailed cost analysis revealed the true economics of construction equipment durability. European machines required major repairs every 800 to 1,000 hours, typically involving frame welding, hydraulic system overhauls, or transmission rebuilds that cost $15,000 to $20,000 per incident. American machines operated past 3,000 hours with nothing more than routine maintenance consisting of oil changes, filter replacements, and minor adjustments that rarely exceeded $500 per service interval. Word of Morrison's findings spread through the construction industry with remarkable speed. Contractors facing their own equipment reliability problems shared similar experiences during industry meetings and trade association gatherings. European-designed machines consistently delivered superior performance during initial operation, but failed catastrophically under sustained American working conditions. The pattern was unmistakable. Optimization theories that worked brilliantly on German test tracks collapsed when exposed to the relentless punishment of American construction schedules. Morrison's testimonial became legendary among contractors struggling with equipment decisions. The German machines were engineering marvels when they worked, he would tell anyone who asked, but they worked only under ideal conditions that rarely existed on American job sites. American machines were engineering hammers that always worked, regardless of weather conditions, operator skill levels, or maintenance quality. His mathematical comparison was devastating to European efficiency claims. Despite costing 35% more initially, American over-engineered machines delivered 40% lower total operating costs over their service lives. The vindication extended beyond individual contractor experiences to broader industry recognition of American engineering philosophy. Equipment dealers who had initially embraced European efficiency concepts began questioning optimization theories that ignored real-world operating conditions. Manufacturers reconsidered design specifications that prioritized initial costs over long-term durability. The momentum was building toward a fundamental reassessment of what constituted superior earth-moving equipment, though the full implications would not become apparent until contractors calculated total lifetime costs, rather than focusing on initial purchase prices and first-year operating expenses. The recession of 1958 struck the construction industry with devastating force. transforming equipment purchasing decisions from engineering considerations into survival mathematics. Major contractors who had weathered the post-war construction boom suddenly found themselves scrutinizing every expenditure as federal highway funding slowed and private construction projects evaporated. Equipment dealers reported inventory buildups as companies delayed purchases and extended existing machine service lives rather than investing in new scrapers. The economic pressure created an opening for European consultants to launch their most aggressive campaign yet against American over-engineering philosophy. Dr. Heinrich Müller capitalized on the financial crisis by presenting detailed cost analyses that seemed irrefutable under recession conditions. His presentations at contractor association meetings emphasized upfront capital savings rather than long-term operating costs. European-designed scrapers cost 35% less than American over-engineered equivalents, he argued, allowing companies to purchase more machines with limited capital budgets. The mathematics appeared compelling to contractors facing cash flow problems and uncertain about future project availability. Muller's campaign gained momentum through trade publication advertisements that featured stark cost comparisons between American and European approaches. Full-page spreads showed identical earth-moving tasks performed by machines with dramatically different purchase prices. The European models moved the same cubic yardage for significantly lower initial investment, a message that resonated with financially stressed contractors who could not afford to consider 5-year total cost projections when they needed to survive the next 6 months. Several major contractors switched to European-designed equipment during the recession, creating a cascading effect throughout the industry. Morrison Construction, despite Jake Morrison's detailed field experience favoring American machines, found itself under intense pressure from corporate accountants who questioned spending premium prices for over-engineered equipment when lower-cost alternatives were available. The company's board of directors, facing their first annual loss since 1946, mandated cost reductions that included equipment purchasing policies favoring lowest initial price regardless of long-term durability considerations. The financial pressure reached into manufacturing facilities where American companies had committed to over-engineering philosophy. At Caterpillar's Peoria plant, internal cost accounting studies revealed that DW21 scrapers cost 43% more to manufacture than European licensed competitors. Corporate accountants presented William Naus with detailed analyses showing how material cost reductions could improve profit margins and competitive positioning. The pressure was relentless and specific. Reducing frame steel thickness from 1 inch to 3/4 inch would save $800 per machine. Eliminating half-inch gussets in favor of 1/4 inch reinforcement would reduce manufacturing costs by another $600 per unit. Naus found himself defending engineering decisions that seemed increasingly difficult to justify through financial analysis. His arguments about long-term durability and field reliability carried less weight than spreadsheet calculations showing immediate cost savings. Corporate executives questioned whether American contractors truly needed machines built to survive 20 years when 5-year financing terms made replacement economically attractive. The European model of planned obsolescence through precise engineering appeared more profitable than American traditions of building equipment to outlast the companies that purchased it. Even within LeTourneau's Longview facility, the recession created internal debate about engineering philosophy. Richard LeTourneau, RG's son who would inherit company leadership, possessed formal engineering training and business education that made him sensitive to competitive market realities. His systematic analysis suggested that electric wheel technology, despite its technical superiority, might prove commercially unviable if customers could purchase adequate earth-moving capacity for significantly lower initial investment through European designs. The industry crisis deepened when several high-profile contractors publicly abandoned American over-engineering in favor of European optimization. Turner Construction announced a fleet modernization program featuring exclusively European-designed scrapers, citing 40% lower capital costs and 15% better fuel economy. The company's press release, widely reprinted in trade publications, declared that modern construction demanded scientific equipment selection rather than traditional American excess. The announcement sent shockwaves through American manufacturing facilities. where workers questioned job security if major customers embraced foreign engineering philosophy. R.G. LeTourneau's re-entry into earth-moving equipment faced the most skeptical reception of his career when his 5-year non-compete agreement expired in late 1958. Dealers who had enthusiastically promoted LeTourneau innovations during the 1940s and early 50s now questioned market demand for unconventional electric wheel machines that cost 60% more than European alternatives. Equipment financing companies expressed reluctance to provide credit for experimental designs when proven European models offered lower risk and better resale value projections. The skepticism reached its peak during the National Equipment Dealers Association convention in Las Vegas, where LeTourneau unveiled his latest electric wheel prototype to a lukewarm industry reception. Trade magazine coverage was politely dismissive, describing the machine as an impressive engineering exercise unsuited to modern economic realities. One editorial in Construction Equipment magazine captured the prevailing industry sentiment with brutal directness. LeTourneau's dinosaur engineering belongs to World War II, not the modern construction age. Contractors need affordable productivity, not museum pieces built to survive nuclear attack. The criticism stung LeTourneau, who had never faced such widespread industry rejection of his innovations. His electric wheel concept represented the culmination of decades spent developing earth-moving solutions, but recession economics had transformed engineering excellence from an asset into a liability. Contractors needed machines they could afford to purchase, rather than machines they could afford to own for 20 years. The distinction proved devastating to American over-engineering philosophy during the industry's darkest financial period since the Great Depression. By year's end, American earth-moving equipment manufacturers found themselves defending design traditions that appeared increasingly obsolete. European consultants had successfully reframed the engineering debate from durability versus efficiency to affordability versus excess. The momentum seemed irreversible as contractors embraced optimization theories that promised immediate cost savings rather than long-term value. The vindication of American over-engineering would require time that recession-stressed companies could not afford to wait, leaving the industry's most fundamental engineering philosophy vulnerable to abandonment just as interstate construction was accelerating toward its most demanding phase. The vindication began quietly in 1965 with maintenance records that told a story no marketing campaign could fabricate. 7 years after the recession had driven contractors toward European-optimized equipment, detailed service logs revealed patterns that fundamentally challenged efficiency optimization theories. Jake Morrison's meticulously kept records showed his American over-engineered scrapers averaging 12,000 hours before requiring major overhaul, while European design machines averaged 6,500 hours before experiencing catastrophic frame fatigue or hydraulic system failure. Morrison's documentation had evolved into the construction industry's most comprehensive long-term equipment study, tracked across multiple interstate projects from Nebraska to Colorado. His European-optimized scrapers, initially celebrated for their superior fuel economy and faster cycle times, had required frame rebuilds at an average of 7,000 hours due to stress cracking along optimized sections. The repairs typically cost $18,000 to $22,000 per machine and required 3 weeks of downtime that European engineers had never factored into their efficiency calculations. Meanwhile, Morrison's American machines continued operating with original frames showing wear but no fatigue cracks. The massive 1-inch steel plate construction and half-inch gussets that efficiency consultants had dismissed as wasteful excess proved prophetic in their durability. Simple cable control systems functioned reliably, while sophisticated European hydraulic controls required constant attention from specialized technicians whose labor costs had never appeared in initial optimization projections. The mathematical reality became undeniable when contractors began calculating total cost of ownership rather than focusing exclusively on initial purchase prices. Morrison's analysis, presented at the American Road Builders Association convention in Chicago, delivered devastating conclusions about European efficiency claims. Despite costing 35% more initially, American over-engineered scrapers delivered 40% lower cost per cubic yard moved over their operational lifetimes. The difference resulted from fewer major repairs, longer service intervals, and the ability to operate under conditions that disabled optimized equipment. Turner Construction, which had publicly embraced European designs during the recession, quietly began purchasing American equipment again after experiencing catastrophic frame failures across their fleet of optimization-designed scrapers. Internal company memos, later leaked to trade publications, revealed that Turner's European machines had required complete frame reconstruction at an average of 8,000 hours, transforming the promised cost savings into massive, unexpected expenses. The company's equipment manager privately admitted that European designs worked brilliantly under ideal conditions, but collapsed under the punishment of American construction schedules. The broader industry recognition accelerated as interstate construction reached peak intensity during the mid-1960s. Contractors working multiple shifts to meet federal deadlines discovered that European machines simply could not survive the relentless pace of American infrastructure development. Optimized components designed for 8-hour European workdays failed catastrophically under 16-hour American schedules. Hydraulic systems calculated for temperate climates broke down in Arizona heat and Montana cold. Transmission components sized for efficiency could not handle the shock loading that occurred when inexperienced operators made mistakes that American machines forgave through massive over-engineering. R.G. LeTourneau's electric wheel concept, dismissed as economically unviable during the recession, experienced remarkable rehabilitation as contractors discovered the true value of unstoppable reliability. His 13-foot-tall tires housing 90-horsepower electric motors delivered torque that never stalled under load, regardless of ground conditions or operator skill. The 12-mile-per-hour maximum speed that critics had mocked as inadequate proved ideal for construction applications that valued consistent performance over theoretical cycle time optimization. LeTourneau's vindication became complete when major contractors began specifically requesting electric wheel machines for the most demanding projects. The massive planetary drives sized for farm tractor speeds created torque multiplication that European high-speed designs could never match. Contractors working in frozen northern conditions found that LeTourneau machines continued operating when European scrapers stalled in conditions their optimization calculations had never considered. By 1970, the construction industry had fundamentally reassessed its understanding of equipment efficiency. Trade publications that had celebrated European optimization theories during the recession began publishing detailed studies showing the superior economics of American over-engineering. The mathematics were irrefutable. European machines moved more cubic yards per hour during initial operation, but required replacement or major reconstruction after 6,500 to 8,000 hours. American machines moved adequate cubic yardage consistently for 12 to 15,000 hours, with minimal major repairs. The long-term vindication extended beyond individual contractor experiences to broader recognition of engineering philosophy differences. European precision optimization worked brilliantly in controlled environments with skilled operators and scientific maintenance schedules. American over-engineering worked adequately in chaotic environments with exhausted operators and deferred maintenance. The distinction proved decisive as interstate construction revealed which philosophy survived real-world conditions rather than theoretical projections. Dr. Heinrich Müller's efficiency theories, so compelling during recession conditions, collapsed under the weight of accumulated field evidence. His optimization calculations had assumed ideal operating conditions, skilled operators, and regular maintenance that rarely existed on American construction sites. The German approach of building machines to exact specifications worked perfectly when those specifications matched actual operating conditions but failed catastrophically when reality exceeded theoretical parameters. The ultimate vindication would require decades to fully manifest, but by 70 the pattern was unmistakable. American contractors had learned to calculate equipment value through total lifetime costs rather than initial purchase prices. The lesson was expensive but decisive. Scientific optimization that ignored real-world operating conditions was not optimization at all, but rather expensive precision that collapsed under practical application. American overengineering, dismissed as wasteful excess by European consultants, proved remarkably efficient when measured across the operational lifetimes that mattered to contractors building America's interstate highway system. The infrastructure project that had seemed impossible in 1956 was nearing completion by 70, built largely by machines that embodied R.G. LeTourneau's fundamental philosophy. The challenge was not the size of the project, but the smallness of the machines. American engineers had built equipment larger than the problems they were meant to solve, while European engineers had built machines exactly the size of theoretical problems that never matched construction reality.